Today we have Richard East talking to us about the ZXH calculus and spin networks. So, go ahead.
All right, thanks for having me. And okay, so in advance, to describe this work in an unusual way as like the first author on it. I mean, with research stuff, it's obviously often forest and trees, and you don't really see much of the forest, and you're working with trees. I would describe the trees here, at least from my personal perspective. It's very boring, but the forest is worth it. And I hope to be able to show you sort of the route through what we did and also why we did it. On the way, there's a lot of constants, a lot of things with combinatorial origin that pop up. If you want to know more about that, I would go to the paper itself. I'm going to bring them up, but I'm going to sort of align the details, basically to make this as clean as possible and understanding well, why and the route rather than the extreme gory details. Okay, so what exactly am I talking about? So we have things that are like the objects at the top, and we're going to, they are 3GM Wigner symbols, which I'll go into the detail of in a second, depicted as something called Yutsis diagrams, which is alternatively anglicized to Yutsis occasionally. And I did have a version of this talk where I wanted to put juicy across the center of the screen with one of these diagrams involved, but I held myself back. But I want you to know I did that for you. If this was just me, it would have definitely happened. And we're going to take diagrams of this form, and we're going to relate them somehow to these objects in the middle, which are spin networks. And these are famous from Penrose, and again, more details are to come. And then finally, through this link between these Yutsis diagrams and these spin networks, I will talk about how we bring it all together in terms of ZX and make these sort of ZX spin networks, linking these two worlds together. Okay, so to explain exactly what those objects are again in a little more detail, let's first look at the Yutsis diagram. So as I said, it represents something called a 3GM Wigner symbol. What is a 3GM Wigner symbol? It's kind of like a Clebsch-Gordan coefficient, if that means much to you. It's a way of decoupling larger spin Hilbert spaces into smaller component spaces. Although while with Clebsch-Gordan coefficients, this is often the idea that you have, spin 1, spin 3 over 2 coming together to make something. The Wigner symbols are more symmetric. So it's more like partitioning the entire space into little clumps. Now, this Wigner symbol, the thing on the left here at the top, this looks like a matrix. To warn you in advance, it is not a matrix. When you put in the numbers for each of them, it should evaluate to a specific number, because they are the coefficients in this formula at the bottom here that tell you how things relate. However, if you leave out the m's in the Yutsis diagram, then it does have a sort of matricial structure. Because in this case, you're talking about the various m's that could happen. What would you get? And the way these j's and m's relate, the j's give you the total spin of the spaces involved. So you'll spin 1, spin 3 over 2, whatever else. And the m's determine the magnetic index. So for example, if you have spin 1, you have 3 different magnetic indices you might have, 1, 0, and -1. And the same thing goes for the other spins. Okay, so with that in mind, what is a spin network diagram? So as I said earlier, you have these things famously invented by Penrose, and they're decomposable into something called the binor calculus, which is sort of the basic meat from which these spin networks can be generated. And they are also sort of tensor network style things. And you can already start to see how maybe you think about how ZX can be brought into the mix. Now, important properties of these diagrams is you view them as open graphs where the edges are labeled with spins, but not any spin will do. You have to obey certain conditions known as the Clebsch-Gordan conditions. And they basically tell you what spins can be around what vertex. And finally, you have ZXH-diagrams. So I'm presuming everyone here has a fairly solid background in ZX, so I won't be going into that in too much detail. But the H part, I will bring up the relevant details about that to come, but it's not a massive part of this. It's more of a technically useful thing. So here what we can see is a ZX diagram with shorthand applied to the wires. And you can view these, this shorthand basically says here, there is a symmetriser, what we'll call it. And basically it projects the input into its symmetric subspace. More details on that to come. That's the only difference from the normal ZX diagram you're seeing here. Okay, so there's a route, there's some things brought up. I said I'm going to connect them somehow, like why? The answer is gravity. Now, this sounds absurd because I've not brought up anything that sounds remotely gravitational, even remotely gravitational, but there is a route to this. And the answer is the use of spin networks in modern loop quantum gravity. Now, what I'm describing here is absolutely not everything you need to know to go from a 4D space-time manifold, that is, standard stuff you'd see in general relativity, and to arrive at why you'd look at a spin network. But I just want to nail some key points that take us from the beginning to the end. So if you imagine you have this world around us, normal classical gravity, the idea is it's in a 4D space-time manifold, some other properties to it, but not particularly interested in right now. What you can do is you can foliate it into slices of time. This is probably unshocking to you, but the actual choice of foliation in this particular structure doesn't matter so much. But what we can do is do this, that we can separate space-time into slices. And once we've done that, there's a way of representing these slices in a way that moves us closer to something that looks like canonical quantization. I say closer, but not exactly to, because there's still a lot of work. So you've got this idea, we've got space-time, we've sliced it up, and we've done something strange to the spaces, but bring us closer to something that's easy to quantize. Now, there's a bit of truncation, a bit of mathematical mess along the way, but the end result, once you do this quantization, is that resultant state space is a set of closed paths carrying representations of SU2. The basis of such a space are spin networks. And that is why this is of interest in the gravity direction, because what we're talking about is representing the fundamental states of quantized space in terms of a qubit calculus. So we're bringing together that sort of the KISS stream at the moment for that consortium of linking the sort of quantum information perspective with the sort of fundamental elements of quantum gravity, at least loop quantum gravity. That's why we're doing this. Okay. So here's a little picture of how to maybe think about this in relation to a spin network. It's not totally accurate, but you've got the idea of there's a vertex and it represents a certain volume, and these volumes are connected by a certain spin, and that spin determines the size of the edge they share. And that's how you should think about it. The vertices determine the volumes that you have in this in your 3D space, and again, the spins determine the area. Okay, now leaving this behind and getting to the meat of what's in the paper. First up, we need to talk about intertwiners. So if you have two representations of a group and a linear map between them, it's an intertwiner if it commutes with a group action. Now, this is already starting to look nicely categorical, and I'm sure some people are very excited about this. And indeed, you can see that these things relate to Hom spaces between V and W in relation to this group. And interestingly and importantly, these are invariant under the group action. So this space we've just talked about of intertwiners, it is the invariant subspace of a Hilbert space with respect to that group action. So if you apply the action of a group to elements of the intertwiners, nothing will happen. You'll get the same thing in and out. And this is all often shared very abstractly. It doesn't naturally link to the 3GM symbols, but we'll see later, viewing it for the ZX-calculus, we can make this very concrete indeed. But okay, moving on from this, what is an example of an intertwiner? So it is the 3GM symbol. The 3GM symbol is an example of how you can decompose these spaces in a way that respects the group structure. And as I said earlier, this here is this evaluates to a number on the left once you've filled in everything, and it's represented by this Yutsis diagram on the right. Though if you leave out the magnetic indices, it does become more matricial, which we'll bring up later. Okay, so here is our Yutsis diagram definition, and here is how it links to the 3GM symbols. If we take these diagrams and we invert one of the wires, now this varies in literature a little bit, but the convention we take, which is the original one, is that you flip the sign of a magnetic index. So if we have a diagram written like this, and I turn one of the wires down, whatever I've written here, it means that the Wigner symbol it represents has that spin, that M1 spin, turned around, inverted. Now, what more relations exist for these diagrams while we try to understand their properties and how perhaps they can link to the string diagrammatic forms of quantum information that we're familiar with? So there are sort of cup and cap and wire-like structures. So again, what we're going to do is we're going to take the diagram, we're going to alter some element of it. Here, what we've done is we've taken the J2 space and we've said it's 0. That's not to say it's magnetic index 0. Literally, the space is 0, so it doesn't exist. And in doing this, there's a representation of that gives us a sort of cap-like structure. And also, we've got these wires that can be represented in a couple of ways in the literature that give us these string diagram wires that we're familiar with. And that's really what I'm trying to point out here, that all this Yutsis diagram stuff has quite a nice relationship with string diagrams we're familiar with. We can also take the trace, and we can compose things. So if you take two 3JM symbols, you can sort of put them next to each other, and that's sort of the multiplication of the numbers they represent. You can also compose them together by joining their outgoing and incoming wires. And the way you do that is you take two Yutsis symbols, 3JM symbols, you invert one of their wires, and then you join them together, which involves summing over the magnetic indices involved on those two spins. So note these spin spaces have to be the same size for this to happen. So now we're seeing that we've got these Yutsis diagrams. They've also got a way of composing, which is also very similar to string diagram stuff we've seen before. And here's just me pointing out that you've also got some inversion rules that indicate certain phases appear. The reason I'm bringing this up is because when it comes time, at least in a paper, if you want to go into the gory details, to really knit together how to make this match up with ZX, you have to pay attention to these phases and make sure that everything, all the rotations are in place to make sure you get these things to line up. This is probably the nastiest part of this work, is doing all the bookkeeping to make things gel properly. Okay, so we've had these symbols with outgoing wires left intact, which means essentially you can have different M's involved. But I hinted at the fact that when you join wires together, you sum over the magnetic indices involved, which means you can get these sort of total invariant symbols. And here is the smallest example, which is the 6J symbol. And you can view this as two 4JM symbols combined, or 1, 2, 3, 4, of course, 3JM symbols combined. And it's often denoted like this on the left, and here's the sort of Yutsis picture on the right. Now, this is another place where we can call back to theoretical physics and show that there is this slightly odd link to gravity. So a very long time ago now, Ponzano and Reggie saw that the 6J symbol approximates the action of general relativity in the semi-classical limit. So if you take this 6J tetrahedron we've just seen, with the labels Ji as its lengths, then its volume in the asymptotic limit is tied to the action that you would see for the 3D simplicial approximation of the Einstein-Hilbert action. So that's to say, if you take general relativity, you apply the sort of simplicial triangulation scheme that you would see in Ponzano and Reggie's work, then the action here is tied in a slightly mysterious way to the limit of these 6J symbols. And I'm just bringing this up to tie you back to this theoretical physics motivation that sort of floats in the background. Now, we've talked about a 6J symbol, but it's also a 15J symbol. The reason I bring up this specific one, although I won't go into detail with it, is with more modern loop quantum gravity, this symbol is quite important. This ties into things like transition functions, transition maps between two states of space and things like this. So this is important for calculating probabilities and moving from this sort of space-time to that sort of space-time. I'm not going to go into details on this again. I just want to make these connections clear so you have in your mind that there is this link between things. Okay, so I talked about if you dropped the magnetic index, then things become a bit more matricial. So this thing on the right is now a matrix. What you're seeing here, you've got two spin half spaces, and I'm not labeling which magnetic index, going to a spin one space. Now, in the literature, there's not so much interest in representing these things directly as matrices. But one of the things that we're going to do, or at least one of the things we do in the paper, is we try and tie things into physics and using ZX in this way. So we need to come up with a convention. What's input and what's output? And the way we do that is we say, okay, if wires are incoming, we say these are input, and the wire is outgoing, we say it's output. And this will give us the shape of the matrix involved, but not the specific elements in the matrix. That is to say, here we can see that we've got two spin half spaces. So we've got 4 spaces along here. Well, it's 4 long, 2 qubits. And we've got a spin one space as outgoing. So this has a depth of 3, if that makes sense. And the fact that we've moved to the spin one representation here as a basis, this will cause problems later and is a fairly large obstacle to quick understanding, but we'll bring up how this relates to the ZX and qubit picture a little bit later. Okay, so I'm saying when you drop the magnetic indices, you can represent these things as kind of matrices, mapping between, okay, if you have this magnetic index and these spaces, where will that send you on the outgoing space? Just to point out what I was saying, if you turn these wires around and you're going inwards, we say that this has a certain representation as a matrix. So here you're seeing the matrix has been deformed into a line versus the matrix shape it was before. That's all I'm trying to highlight. Okay, and now for something rather similar. Penrose binor calculus. So now I'm going to show you a different diagrammatic representation. And I'm going to use it to link things to the ZX calculus in the end. It's going to be our route from the Yutsis diagrams to spin networks, and finally also to the integration with ZX. So Penrose binor calculus has the following rules. It looks like the sort of cups and caps you're used to, with some variations and some eyes in some strange places. But already you can probably imagine these are going to be the wires you're used to with some rotations on them. Okay, it's also got some trace properties and something called the binor relation, which some of you may be familiar with. Now, when you have a spin half system like this, well, when you have spin half wires, like the ones we just saw in the previous, there's only single state Dirac input and output. If you want to move to higher spins, there is a way to do this in the binor calculus, which relates to how we'll do it in ZX and how I've talked about these things in the past. If you take n binor wires, which you could see as qubits, if you like, with some rotations on them, and you project to the symmetric subspace, then you get the higher spins. Specifically, if I take n spin halves, then I will get spin n over 2 when I take the symmetric subspace. That is literally the space it takes you to. And all this is built on representation theory of SU2. Now, with that in mind, and how Penrose links the sort of qubit spin half wires to the higher wires, we can now start to imagine, if we can find a link between binor calculus to Yutsis diagrams, how we start connecting these dots. Okay, so literally in line with what I was just saying, on the left here, we have the higher spin network wire. That is, well, I'm jumping ahead of myself there. Here we have the largest spin wire in the binor calculus. And on the right, we have the Yutsis diagrams, the Yutsis diagram wire. And as we can see, there's certain constants in between them of combinatorial origin, but they do relate to each other. Now, to bring things closer to a sort of Yutsis style structure, the Penrose binor calculus has trivalent vertices. And what's interesting is when you look at them in the sort of spin half space, the Clebsch-Gordon conditions, which one imposes in spin networks, which is where all this is going, are naturally encoded. That is to say, if you stare at it long enough, perhaps you can convince yourself, the Clebsch-Gordon coefficients literally determine when it is possible to write down an interconnected set of vertices, set of wires like this. If you do not meet the Clebsch-Gordon coefficients, you do not have enough wires to pair up. That's all that happens. The Clebsch-Gordon conditions viewed at this spin half level simply tell you that everything has to connect up. Otherwise, it's not well defined. I mean, it's not the symbol that you were saying it was. And I think that's a nice property here. When you look closely at the spin half structure, the qubit information structure, some things become very natural very quickly. Okay, so we've got this trivalent vertex thing. It's probably starting to look a bit like Yutsis symbols in your mind, but you know that they don't quite match up. So let's work in that direction further. So there's a certain norm for these things. If you take these binor trivalent vertices and connect them together, you get this norm. And this norm is our way to connect things up with the 3GM symbol. You can come up with this relation. So I've left off the J's and M's. I'm basically saying the trivalent vertex on the left is proportional to the Yutsis symbol multiplied by this normalization constant. Now you'll notice on the right there are arrows, which and there aren't arrows on the left, which probably sets off alarm bells in your head. But in binor calculus, usually there's an implicit orientation to things. So that's the reason you don't see any arrows determining things on the left-hand side. Okay, so now we've got our Yutsis diagrams on the right, and we've got these binor calculus relations on the left, which break down into qubit spin half wires. That's very key for us. That's sort of our way in. Now, how does this relate to spin networks? So spin networks you can see in a couple of ways. You can view them as the binor calculus sort of seen from a distance. Those trivalent vertices, if you step away then and fuse all those down into thick wires, then all you're saying with these 3/2, 1, 2, you're just saying what number of wires are going into the vertex. And again, those Clebsch-Gordon conditions, now we know all they say is these need to match up. So for spin 1 here, we're going to, that's going to be 2 wires, because it's 2 wires to get to spin 1. 3/2, it's going to be 3 wires. And this is all this, when you view things up close, this all becomes very clear. Now we can also see these as related to Yutsis diagrams now. Each vertex has ties to this Yutsis diagram structures. So you can see that every every vertex can be seen as this SU2 group invariant in the case of SU2. In the case of 3GM symbols, SU2 is a group of interest. They are invariant under SU2 rotations. So you've got this link between spin networks and binor calculus and Yutsis diagrams. Now, let's do something with this. So let's take a wire in Yutsis diagrams and say, okay, what is this as a ZX diagram? And this is quite easy to do for us, right? We just need to look at the matrix and say, what do I need to do to my ZX wire to get what we want? So in the single wire qubit wire, if you like the case, it's easy. We just add a green pi rotation. If we go to a higher spin, we have these green pi's involved again, and this is going to be a theme all the way along. But now we need to symmetrize over the space. If you look closely at the spin 1 Yutsis wire, it is in fact the symmetrized spin wire with a phase rotation on it. That is to say, just like in binary calculus, the higher spin wires are the projected subspace of multiple qubit systems. And this thing here on the right, this is exactly what that does. That is a symmetric projector acting on 2 spin half spaces. To see that a little more closely, and here's to bring up the ZXH-ness that you may have concerned you all the way along. If you look at the top diagram here, well, I'll flick back for a second. The key thing to point out is this is green here, and a green is a plus state, you may remember, which is equal to the 0 plus 1 state. So you could view it as this diagram added to this diagram with scalars involved, of course. So when we have this red here, by looking at the only ZXH rules you need to concern yourself with, the explosion rule and the absorption rule, you can see here that this takes in the red and it explodes into a bunch of greens. And you see after a few reductions, all very normal ZX ones, you get the identity wires. On the other hand, if it's a pi, the topology is quite different, literally the diagrammatic topology. It gets absorbed in, and if you do enough rewrites, again, ZX ones, you see that it's a swap. So here we're seeing this projector, this object we've attached here, is a summation of doing nothing and swapping them over. And if you think about it, what would the projector to a symmetric subspace do? Exactly this. Because if you add doing nothing to swapping them over, then the anti-symmetric parts by definition will cancel, leaving only the symmetric parts. So that's what we've done here with the spin 1 wire, well, the Yutsis 1 wire. It is basically a spin 1 space with some phase rotations going on. Okay, and we can go to higher spins. Basically, all these do is encode larger permutations. So before we only needed to do the identity and a swap. To get every permutation over 3 wires, it's slightly more complicated. For more details on this and the constants involved, see the paper. But here I just want to point out there's a ZX way of rewriting these Yutsis wires. Here it is for spin 2. Here it is for spin 5 over 2. Yeah, so you can see the point I'm making. These things are horrific. These are a construction that we have created. There's probably, in fact, we're sure now there is a more elegant way of writing these things down. But there may be even more natural ways to do it, which is something of interest at the moment. But yeah, I just want to highlight there is a way of writing these things in ZXH. Okay. So how do you compose Yutsis wires from the perspective of ZX? So the Yutsis wires themselves, as we've seen, they look like a projector with some green rotations on them with a phase at the front. Now, if you compose 2 Yutsis wires, you need a Yutsis wire again. So you can already see you can't just put 2 together because the greens will cancel. Since they're acting on every wire and all these symmetrizers do is permute things, they can move either side of that permutation. So they will, if you just have one next to the other, move through and cancel, which would mean you haven't got a Yutsis wire again. So the composition rule is a little less trivial than you might imagine. You can't just strap things together. However, it's not too difficult, as you see here. Okay, so we've got an idea of how we compose Yutsis wires in ZX. Now we can talk about cups and caps a little bit. So here we've got various directionalities on Yutsis diagrams with wires going in and out. And here you can see on the right the ZX diagrams that correspond to, where it kept in line with this idea that ingoing wires are input spaces and outgoing wires are output spaces. And we try to keep that all the way along. Okay, so now let's talk about Yutsis symbols. So we've seen this sort of 1 in, 1 out cup and cap version. What if we have all 3 wires, the real thing? How can we represent this in ZX? Well, it looks like this. Here we have an alpha, which is just the constants to rescale the symmetrizers. And in between, we've got the binor calculus normalization constant at the bottom. The reason we've got that is because when we're writing in this spin half form, we're actually working in a sort of version of the binor calculus. So when we need to move to the Yutsis diagrams, we need to use that normalization to connect things up properly. Okay, so now we've got Yutsis diagrams represented as ZX diagrams. We've also talked about how you turn wires around. So here you see that, well, as we discussed earlier, if you turn the wire around, you flip the magnetic constant around. In these diagrams, if you look at it long enough, you can work out that what that requires is you just place 2 red pi rotations here. And this gives you what you want. Alternatively, you can just view this in terms of the cups and cap versions, the input-output cups and cap versions, and reconstruct this diagram on its own without thinking about flipping things around. But it's important that we have both on hand. Now, talked earlier about how things are SU2 invariant. Or at least we said that the 3GM symbols were intertwiners.
Richard?
Yes?
Sorry, I might have missed this, but I can't quite parse what's happening with the dot in the middle of this shape.
I'm so sorry. Yes. So this is just saying there's more wires connecting up. So here you've just got these connecting here and here, but it could be possible that more go through here, or some of them curve round. You can see the hand symbol on my screen.
Yeah.
Yeah. Okay. So you can see this wire goes up here. This wire goes around here. It's entirely possible we'd have more wires. I mean, for higher spins, you'd have more than just 2. This could come up and curl up here. Maybe another one goes around here. So all I'm saying with these 3 dots is there are more wires here. And depending on how things connect up, there'll be different phases that correlate with that.
So
Okay,
there,
but it's not meant to define where those wires go, I guess.
No, it's just saying more wires exist there. And depending on where they connect, you'll get different choices of red and green.
Okay, yeah.
So, is that a little bit clearer? Sorry if that was...
Can I, Richard, can I maybe say something
Yeah,
about
of course, of course.
So, Alex, these numbers 2J1, 2J2, and 2J3 are how many wires are in that block? And then the Krebs-Gordon coefficients are satisfied, the conditions are satisfied, which means there's a unique way to line up all the wires. There's like no freedom of choice there. There's a unique way to line up the wires. And because everything is symmetrized, it doesn't matter in which order you do that. It just matters like how many wires from J1 go to J2 and how many go to J3. But everything sums up exactly right to work out. There's like a unique way to do that.
I see. Okay. So one of these numbers will be big, and it will kind of split into the others. Is that the idea?
Yeah, one of them will be larger.
Krebs-Gordon condition.
Exactly. I mean, if you look at the Krebs-Gordon conditions, one of them is just one of these is bigger than the other 2, plus or minus bits and bobs. And you need that if you're going to pair everything off. I mean, if you're going to have 2 sets of wires coming in, you need a third one that is bigger or equal to the size of both, so you can pair everything off. It's just it has to be.
So
but it's nice again. Sorry.
Is it true that J1 plus J2 equals J3?
Yes, there might be a caveat to that, but it's not immediately popping into my head.
That's not true. The sum of the 3 things must be an integer, because otherwise, the sum must be an integer, and then the differences are like bounded by the size of the other. So like the difference between J1 and J2 must be at most J3, and like for all permutations of J1, J2, J3, that's also true. I think those are the Krebs-Gordon conditions.
Yeah, I mean, it's literally the Krebs-Gordon conditions are what constrains this.
Thank you.
No problem.
Sorry, I just missed. So what does the bar mean? The line.
Sorry?
The lines on the ZX diagrams, the bar.
The bar is the symmetriser. It just says that we've got a symmetric permutation going on here. So you can imagine these wires, these things from before. If we have this is an example of a bar. So it's
all
just a way of
things.
saying these quickly without having to write all of this down.
Okay, they are these kind of things.
Yep, that's all they are.
Okay, thank you.
No problem. Sorry for not being clear about that. I think I said it earlier, but maybe a bit too briefly. Okay, so moving forward, we talked about SU2 invariance again. So we brought up 3GM symbols originally as intertwiners or related to intertwiners. Then we never really talked about that again. And it can often seem a little bit mystical that these have these properties. When you view these diagrams, knowing that what you want is SU2 invariance, they're almost inevitable in the structure of the ZX diagrams. what you want is that if you apply an arbitrary rotation to every input or every outgoing wire, if you like, they should cancel out. They need to be invariant under SU2 rotations. So if I write the group rotations on each wire in ZX, which you do like this, for a group action for higher spins, you just decompose it as the same action over the lower spins, so spin half. And we just need to say that these need to cancel. So you know they're going to need to pair up, and you know you're going to need some phases to flip things around. Now, given the Yutsis construction, there's extra little green pies going on, but you still know that you're going to have this a certain number of greens and reds to make sure things swap over. So if we take, if you're looking at my cursor here, the alpha is going to go through, because it's going to move through that fine. It's going to flip signs, and then it's going to reach here. And that alpha, when it comes through, is going to cancel with it. And a similar thing happens with beta. It goes through 3 green pies, but that's going to give you the negative again. And the same is going to happen with the gamma. This is literally showing us how SU2 invariance will happen when we look at it in a ZX diagram way. Again, this is another way that looking at these things from a ZX perspective, which is really, in this case, I think a quantum information perspective, gives you some properties that look strange very naturally. Okay, so we've talked about having the 3 GM symbols. How do they combine? So it's a bit of a mess of constants, and I invite you to go away and look at the original paper if you want the details of this. Basically, it's a way to normalize the scalars and involve all the binor norms that need to be cancelled out. But in a ZX perspective, we just need to do that Yutsis fusion we talked about before. So we're going to turn one wire around, which meant introducing some red pies, and then we're going to slap the Yutsis fusing relation written in ZX in the middle. So now we've got a way to take our 3 JM symbols written as ZX and build 4 JM symbols. And now we've done that, we can talk a little bit about how we represent things as matrices once we drop the reference to those magnetic indices. So here we're just saying we have a spin half space, a spin half space, a spin 1 space. We're viewing the 2 halves coming in to produce a spin 1 space, but we haven't specified which magnetic indices we're working with. So now it is a matrix on the right hand. And this is where we can start looking at physics. And we did look at physics and say, okay, how do we write these things as maps? What do they look like? How do we work with them? Okay, so here's an example of exactly that diagram before. So again, we've got 2 halves here coming in and a 1 coming out. As a ZX diagram, it looks like this. Now, you will notice immediately, this is too big as a matrix. The reason we've got this is because when we look at this in a qubit basis, the spin 1 space has repeated elements. Because if you think about spin 1, you have written in qubit terms, you have the 0, 0, you have the 1, 1. So that's your spin 1, spin minus 1, written in spin 1 terms. And your spin 0 is the combination of 0, 1 plus 1, 0. It's the symmetric subspace. It's a symmetric element, or the multiplet, depending on which background you have. So we're going to need to do something to project our qubit version of this matrix that we'll get out of physics into the spin 1 space, at least for the output. Looking at the form of this, you might be a little bit confused by the wires crossing over here, which at first for us was also rather mysterious. That's a very natural origin. Going back to this diagram, if we look at the 2 spin halves, if you swap them over, sorry, this is the first space, this is the second space, this is the third space. When you move to this sort of left to right input-output version, the first space, in physics at least, is considered the one at the top. So you're going to need to swap over this first one and move this one down in order to match up properly. That's the only reason we have this swapping going on. It looks very mysterious at first, but it's quite natural. Okay, so as I said before, we're going to need a certain projection. This is the projection of the spin 1 space. So if you have 2 qubits in order to map them to spin 1, this is what you do. And indeed, we see this matrix here, which is correct. This is what you'd expect to see, and you find in the literature or in various computational engines that generate these things. This is the idea that P1 is being applied to this qubit version of the matrix, and this is what you get out on the right. Okay, let's look at something more complicated. So here we've got 2 spin 1s coming in and a spin 1 going out. So again, we're going to have a space in the qubit basis, this is correct, but to match up with things you'd see from various computational engines again, we're going to need to map everything to qubits. This is considerably uglier. We're going to need this thing. And if you stare long enough, you can work out why exactly this is the case, but it is. And when we apply the matrix M viewed as our qubit physics version of what we got from that diagram and apply the various projectors left and right, we get what we expect. And this is the Yutsis diagram once you've dropped the reference to the magnetic indices as a matrix. Okay, so here I've just been making some pretty run-of-the-mill connections between what you'd see in the literature, or if you ran operations on computers to see what these things look like, and how you'll get it out of physics. And the relationship is literally because in quantum information, we're working with qubit bases. When you're working with spins, usually as a physicist, you're working with the spin basis, which is quite natural. Okay, so what about when you put specific magnetic indices in? So you probably guess already you're selecting an element out of that matrix, and ideally that element should match up with the Wigner coefficient that the Yutsis diagram represents. And indeed, that's what we see. So here we've just taken the previous Yutsis, well, we've taken here a 4JM symbol, and we've chosen spin 1, 0, and half and half. So half and half as magnetic indices, you probably know already, this is just spin up. So it's just red circles here with some normalizations going on over on the left. And for spin 1, we have just 0, 0, very easy. The only slightly complicated thing is spin 0. But as I said before, that's 0, 1 plus 1, 0. And if you think for a bit, you'll see that this is the way you represent that. Okay. Now, we have a way of talking about Yutsis diagrams, a way of turning them into numbers. We viewed them as calculations types of electric physics, and we talked about how you fuse them together. So naturally, we can start talking about how you build the 6J symbols, these things that sort of start to relate to quantities of interest in gravity. This is sort of a schematic version of it, depending on where things connect up, as we talked about before. You're going to have these various rotations here. And if we look at a concrete case, here is this specific 6J symbol, and we computed this in physics, and we get the number we expect, just to say that all this adds up and it all works very nicely. Okay. So now talking about spin network diagrams. This is kind of anticlimactic point we reach here. Okay, so now we've got these 3GM symbols. We know how to fuse them together with Yutsis diagrams. We know that such a thing as ZX-diagrams. So the answer is this, it's just the fusion of 3GM symbols and using the Yutsis fusion rule for bringing wires together or matching wires up. So yeah, I mean, you can, as we're pointing out here, there's actually a lot of redundancy in the way you do that. What this redundancy means, I'm not quite sure. I'm not sure how to interpret this fact. But yeah, the raw mechanical construction that we've talked about, this brings us to the completeness. We have this idea of how we represent 3GM symbols. We have a way of combining them. We know that this brings up spin networks. This gives us spin networks. So now we have a way of writing spin networks as ZX diagrams. I think a long time ago, there was some sort of anonymous questions people would like to ask sheet. I believe linking spin networks and Penrose diagrams to ZX was one of the questions on there. So for whoever that was, this is your answer. Now, going a little bit beyond this. Okay, I should add a caveat. John has not seen this. Pierre, I think, has glanced at it. So we're now walking in turf. It is purely me, and I don't want to unnecessarily dirty their good name. But let's push further. We now have things represented as spin networks. And I've told you that spin networks relate to the state space of quantum gravity. If that is true, then as states, there are observables we must be interested in. And indeed, there are in quantum gravity. Now, if we work with Euclidean quantum gravity, I'm just throwing names at this point, but the reason we're talking about this one is because it's state space. The volumes are going to be 4-valent intertwiners, which basically means it's the 4JM symbols. Well, at least that's how we're going to talk about it. So now we know that we have these idea that these vertices are going to represent volumes, and the spin wires are going to represent areas. This is what I talked about earlier in the relation between gravity and this stuff. Let's now ask, okay, well, can I write these operators? Can I write the area operator and the volume operator in ZX as qubit diagrams, as qubit relationships? So in advance, the answer is unsurprisingly yes, because I'm talking about it. This stuff is a little newer, it's not as clean, but I'm going to walk you through it all the same. And Alex, you may appreciate this as this is what you'll be reading shortly. And it contains some corrections, so be wary of that. Okay, so what are you seeing in front of you? Well, the area operator is J squared in loop quantum gravity. J squared here just means we're going to get the sigma x squared, sigma y squared, sigma z squared, and we're going to divide by 4. So as a spin 1 operator, this is actually, as on spin half, this operator is extremely simple. I mean, it's a diagonal in its basis, and with a qubit basis, so everything works nicely. This top diagram reduces. You get a half out in front, and this thing is equal to 6. So we get 3/4, which is exactly what you'd expect for spin half. How do we go higher? So immediately to do this, you run into the obstacle of, okay, suddenly I need to think quite hard about diagrammatic SU2 in the algebra. Not all of it, but a key component that we're going to need is that if you want to do not the group action, but the algebra action of SU2 on a higher spin space, it is not that you just apply the same element to each of the individual spaces that compose it, that is to each of the spin half spaces. What you instead get is this kind of superposition. So if pi is our algebra action operating on, I don't know, spin 1, let's keep it simple, then we're going to see this broken down over the spin halves. What you're going to have is the same algebra action but acting on the first spin half space, plus that algebra action of acting on the second spin half space. This is how the action decomposes. Now here I have my little schematic diagram, which I find quite helpful. You may not, but I'll try and talk you through it either way. The idea is we have this action J on the left, which is acting on a single spin half wire. To raise it to a higher spin, what you need to do is perform the action I just described. You need this J applied in each different position over the spin spaces. Now, on the grounds that that's quite hard to do in ZX, moving the J around, it's easier to move wires about. So this is kind of the, if the mountain won't come to Mohammed, Mohammed will go to the mountain logic. We're going to permute the wires to make sure that we get J applied in all the different places we want it to be applied. So what does this diagram mean? So the one hot function here, this is a notation I've taken from electrical engineering. The idea being it encodes something being on or off simply in the heat of one wire. So in this case, it's either we have 2 wires coming out, if we imagine, well, basically it determines what's on and what's off. And it does this in a very basic way. So if you have a qubit state of 2 elements, only one of those will be 1. And that determines which permutation you're acting on. That's all this top part indicates. So if we're viewing this in a spin half way, okay, now I'll talk about that too. So in the spin half setting, it's fairly simple. We're going to have 2 options. We're going to either permute or we're not going to permute. So if we're not permuting, then we're going to have 0, 0 coming out here. These will do nothing, and J is applied to the top wire. For the 1 state, we're going to have the only other permutation available. These are going to be swaps. You'll see that this wire moves down. The J is now acting on the bottom space, and then it's permuted back down again, so you keep it being the bottom space. And in this way, we get this structure here. I hope that's clear. I'm going to give some examples now of how we can use it. So here is me showing how you build the higher spin Pauli X, Pauli X, the spin X notation. So the spin X itself for half of the wire half is h bar over 2 times this rotation here, as we all know. And here's another 2. This is just correction for the size of these things. And we can show by just going to physics or something that this gives us this matrix. Again, we're in a sort of spin qubit basis here. So if you want to see it in the manner that we're used to, or you'll find in physics textbooks, you have to apply the projectors to spin 1. But indeed, when we do that, we find we get exactly what we expect. And here's me doing it again for the lowering operator, just for a bit of fun. So here we've got the lowering operator written in spin half terms. Here is it raised, where this is that sort of one hot function I talked about earlier. You can see this if you think about it in terms of 0s and 1s, because the bent wire is 0, 0 and 1, 1. So it's kind of 0 and 1 split, so it's applying to both of them at the same time to make sure that when we permute, it's both of them permuted by the same one, and vice versa. Okay, and so you get the matrix we expect. We do the, we project spin 1 space and we get what we anticipated. Even better, we can show the action of something like the lowering operator. So instead of just taking my word for it and using physics, let's do it. So here is 0, 0 here, which is spin +1. And it's going in. We're going to have some various ZX reductions, a couple of cheeky ZH ones, where you have the multi-legged ones that are involved. This is just that explode or absorb rule we talked about earlier. And what you find is you get this state here, which is, as we talked about earlier, spin 0. in the spin 1 basis. So you can diagrammatically see how these common raising and lowering operators, which can look kind of mysterious when seen in seen in matricial form, actually perform their function, which I find nice at least. And you get the correct eigenvalue. Okay, so if you want to move to spin 1 for the area operator, we need to be slightly cleverer, because the j² operator doesn't really exist as an algebra element. J applied to J exists. So it's not actually that you apply sigma x squared, sigma y squared, sigma z squared. What you do is apply sigma x plus sigma y plus sigma z, and then you apply it again. But since we need to raise that by times, it's a slightly more convoluted operator. So each of these is the J operator being lifted. And this object here at the top just determines that, okay, we're applying X when we're applying X, we're applying Y when we're applying Y, applying Z when we're applying Z, just to make sure we get the summation right. And here, since it's sigma X, sigma Y, sigma Z squared is what we're having here, we have a 1/4. We have a 4 to correct the scalars. And there's a 1/2 because this thing is twice too big because of these 2 Hadamard's here. And again, okay, I write down a matrix, project it, and we get what we expect and the eigenvalue to be correct. What's interesting here, well, what's important here rather, is the area operator is diagonal in the spin basis. Where is that not true, I hear you ask? The volume operator, which is considerably nastier. And I'm only going to talk about it for spin half. And this is the last thing I'm going to talk about. So in LQG, a lump of quantized space is written in this form, where you apply it to a 4-valent vertex, but you just take one of those wires to be acted on by the identity. And the smallest possible volume is spin halves everywhere, basically. We're focusing on the meaty part of this at first, the part that does something, isn't just constants, which I've written as this sort of B² thing here. So we're going to need something that looks like this. Why? Well, let's look back. We've got J1 dot J2 cross J3. This, if you remember your various calculus courses from a long time ago, can be written in terms of the epsilon I, epsilon j, epsilon k operator, which is going to be permutations, but with minus signs in certain places. Maybe you recall this. The way you do this is by the same permutation structures we talked about before, where things get permuted and unpermuted, so that you can apply these operators in all the different places you want them to be applied, with these little green pies that induce the -1s when you need them to be there. And that's all that's happening here. And there's a constant in front to say that all this needs to be normalized. Okay, so by direct calculation, I mean, I just put pen to paper, this is equal to this. So I know I can just sort of compare matrices. There's going to be some very crude matrix comparisons that put on here. I haven't tried to be too clever in working out where every constant comes from. So I know that this is this matrix. I know that X, Y, and Z rotations are going to look like these things here. So I know that this is the matrix that gives me this element, and this is the diagram that gives me this element. Okay, so now I have the operator written down. However, I can't just apply it to a bunch of wires and think that's going to work, because, as I said earlier, while area is diagonal in the spin network basis, volume is not. So there should be a plus and minus here, actually, with the I naught. But key point here is that one of the basis elements, anyway, is I naught plus I times √3 times I1. Now, what on earth are these? And these are the different intertwiners that can take you between 2 spin halves to another 2 spin halves. And I've written down the matrix here. It's just to show that that's what it is. Let's talk about what I0 and I1 are. Like I said, these are sort of specific intertwiners, specific choices of how 2 spin halves can be related or not to each other. So they can be utterly disconnected. This is the I naught. And they can be connected. So these are 4 JM symbols, and these are 2 basis choices of the 2 ways you can tie these things together. So here you're seeing they're just coupling off with each other, and here you're seeing kind of identity, and then the Yutsis Y requires a spin 1 in the middle. Because if you imagine, if it's a 4 JM symbol, you're going to half, 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 but that linking wire must be spin 1, and that's what's going on here. Okay, so these have certain structures and matrices. This is how they're represented. Now, I said before it's I0 plus I √3 I1. So unsurprisingly, I have to do some monstrous things to make these things add up together. Before I do that, quite cleanly, the biggest problem is that these have different topology. So I need to invent a little diagrammatic structure, which I've done, to take us from the first one to the second one, to give us a way to have a superposition of one plus the other. and here is unfortunately a bit small. You can see that if you extend, if you imagine that this green is extended out, so we have a green node attached to a green node and think, okay, with a green node going into something, we can view this as a plain red plus a pi red. So you have a plain red here plus a pi red. And then we can see how these two decompose. And look, we have an identity one, which looks rather like I1, and we have this decoupled one, looks like I0. Okay. Then we have to stick in this spin one thing, and we have to deal with the constants, but it can be done. Yeah, that's all I hate to say at this point. It can be done, and it looks like this. So this should be an eigenstate of the operator we just described. Can we show this? Now, diagrammatically, I have not tried, if I'm completely honest with you. But I did want to check I was right. And I would like to validate that basically these structures can be written in this diagrammatic way. You can link the operators of loop quantum gravity to quantum information-like structures as we see in ZX. And here we see me performing a certain eigenvalue calculation, and indeed this is eigenvalue calculation. And when you take the various scalars involved and add in the 8 pi g, h bar, gamma to 3/2, so on and so forth, you get this as the answer to your volumes. You get 2 possible eigenvalues, plus and minus, and this is correct. Okay, so let's conclude. What have I done? We've gone a long way. We investigated the structure of Yutsis diagrams in the binor calculus. We described Yutsis diagrams through ZXH, and we used the bridge from Yutsis diagrams to binor calculus to describe spin networks. And we did this by using a sort of way we could decompose binor calculus while linked to this Yutsis idea of SU2 invariant symbols to give us our spin networks. We developed a way to apply higher spin operators by raising spin half operators. And in that way, we could apply the geometric operators that you might see in loop quantum gravity to vertices of spin networks. And that concludes the talk. And thanks for listening.